To achieve state-of-the-art on HotpotQA, this paper learns graph-based recurrent retrieval method for reasoning paths over Wiki Graph. So today I'm reading paper from 2020, February 14th, Learning to Retrieve Reasoning Paths over Wikipedia Graph for Question Answering. Abstract is answering questions that require multi-hop reasoning at web scale necessitates retrieving multiple evidence documents, one of which often has little lexical or semantic relationships to the question. This paper introduces new graph-based recurrent retriever approach that learns to retrieve reasoning paths over the Wikipedia graph to answer multi-hop open domain questions. Our retriever model trains a recurrent neural network that learns to sequentially retrieve evidence paragraphs in reasoning path by conditioning on the previously retrieved documents. Our reader model ranks the reasoning paths and extracts the answer span, including the best reasoning path. Experimental results show that the state-of-the-art results in a free open domain QA dataset showcasing the effectiveness and robustness of our method. Notably, our method achieves significant improvement in HotpotQA, outperforming the previous best model by more than 14 points. In this paper, we introduce new recurrent graph-based retrieval method that learns to retrieve evidence-based documents as a reasoning paths for answering complex questions. Our method sequentially retrieves new evidence documents, given the history of previously retrieved documents, to form several reasoning paths in graph of entities. Our method then leverages an existing reading comprehension model to answer questions by ranking the retrieved reasoning paths. The strong interplay between the retriever model and the reader model enables our entire method to answer complex questions by exploring more accurate reasoning paths compared to the other methods. To be more specific, our method, sketched on Figure 2, constructs Wikipedia paragraph graph using Wikipedia hyperlinks and document structures to model relationships between paragraphs. Our retriever trains a recurrent neural network to score reasoning paths in this graph by maximizing the likelihood of selecting a correct evidence paragraph at each step and fine-tuning the paragraph BERT encodings. Our reader model is a multitask learner to score each reasoning path according to its likelihood of containing the extracting the correct answer phrase. We leverage data augmentation and negative example mining for robust training of both models. Overview. This paper introduces new graph-based recurrent retrieval method that learns to find evidence documents as a reasoning path for answering complex questions. We then extend an existing reading comprehension model to answer questions given a collection of reasoning paths. Our method uses strong interplay between retrieving and reading steps, such that retrieval method learns to retrieve set of reasoning paths to allow to narrow down the search space for our reader model for robust pipeline process. Figure 2 sketches the overview of our QA model. We use Wikipedia for open domain QA, where each article is divided into paragraphs, resulting in millions of paragraphs in total. Each paragraph is considered as our retrieval target. Given a question Q, our framework aims at deriving its answer A by retrieving and reading reasoning paths, each of which is represented with sequence of paragraphs. We formulate the task by decomposing the objective into the retriever objective, the select reasoning path, and relevant question, and the reader objective that finds the answer. Okay, let me find conclusion. Conclusion. This paper introduces a new graph-based recurrent retrieval approach which retrieves reasoning paths over Wikipedia graph to answer multi-hop open domain questions. Our retriever model learns to sequentially retrieve evidence paragraphs to form a reasoning path. Subsequently, our reader model re-ranks the reasoning path and it determines the final answer as the one extracted from the best reasoning path. Our experimental results show significantly advance the state-of-the-art on HotpotQA by more than 14 points absolute gain on full wiki settings. Our approach also achieves the state-of-the-art performance on squad open natural questions without any architectural changes, demonstrating the robustness of our method. Our method provides insights into the underlying entity relationships, and the discrete reasoning paths are helpful in interpreting our framework's reasoning process. Future work involves the end-to-end training of our graphs-based recurrent retriever and the reader for improving upon our current two-stage training. Alright, let me check if they have some nice examples here. And no, I don't see them right here anywhere, maybe in appendix. So this was the spice of the paper that must always flow, and I will go now more into the detail. I will find some examples, I will read part of the introduction, and I will also try to, this time, look more into the detail. If you'd like to continue, please continue. I'm interested myself, and yeah, please dislike and unsubscribe, and yeah. Okay, and yeah, if you leave now, I hope to see you next time, but now I continue. So we're gonna look for some examples here as well. Okay, so an example from natural questions open. The bold text represents titles and paragraph indices. Denotes, for example, 1 denotes the paragraph is an introductory paragraph. The highlighted phrase represents the bridge entity, and the text in red represents the answer span. Okay, so the paragraph 1. Roberta Flack. Roberta Cleopatra Flack, born in February 10th, 1957, is an American singer. She is known for her #1 single, "The First Time Ever I Saw Your Face," killing me softly with his song. So the killing me softly with his song is highlighted in yellow. And then the second part is killing me softly with his song. 5. The song was written in collaboration with Laurie Lieberman, who recorded the song in late 1971. The 1973 it became #1 hit in the US and Canada for Roberta Flack. Many artists have covered the song. Annotated reasoning path. Killing me softly with his song. 5. Predicted reasoning flag. Roberta Flack goes to killing me softly with his song. And the question was, who sang the original version of Killing Me Softly? Okay, so when they pose this question, apparently they find the reasoning path that they first find the Roberta Flack, they find this paragraph, and there's the song name, and then they have the song name theirs, and they using the song name they go into more detail, and then they again find the Roberta Flack. I guess that's how they do it. Okay, so let's go back to introduction. Okay, another example. Q question, the bridge. Before I go to sleep, stars, and I'm Australian actress, producer, and occasional what? What? I don't get the question. Before I go to sleep, stars, and Australian actress, producer, and occasional what? Okay. So, the first paragraph here is before I go to sleep, film. Before I go to sleep is a 2014 mystery psychological thriller film written directed by Romanov. And then they find that the film stars Nicole Kidman and other actors. Then next paragraph is Nicole Kidman. Nicole Mary Kidman is an Australian actress, producer, and occasional singer. Okay, so here we have the answer in red. So, annotated reasoning path. Before I go to sleep, film goes to Nicole Kidman. Predicted reasoning path, Nicole Kidman. Q, comparison. In between the Bears and I and Oceans, which was released on July 31, 1974 by Blue Vista Distribution. Bears and I. The Bears and I is a 1974 American drama film directed by Bernard McEventy and written by John Whedon. The film stars Patrick Wayne and so on and so on. Oceans. Oceans is 2009 French nature documentary film directed, produced, co-written, and narrated by Jacques Perrin with Jacques Clouseau as co-director. So annotated reasoning path is the Bears and I, Oceans film. Predicted reasoning paths, the Bears and I. And the original question was, in between the Bears and I and Ocean, which was released on July 31, 1974 by Blue Vista Distribution. So distribution. Okay, so which of the two, the Bears and I and the Ocean, which of them was released on July 31, 1974? I mean, the questions are written really, really strangely. It's sometimes hard to understand what they mean, but I guess the model is doing quite well then. Introduction. Open domain question answering QA is task of answering a question given a large collection of text documents. For example, Wikipedia, most of the state-of-the-art approaches for open domain QA in 2017, Bank 2018, 2019 leverage non-parameterized models, TF-ADF or BM25 to retrieve fixed sets of documents where an answer span is extracted by neural reading comprehension model. Despite the success of these pipeline methods in single hop QA, whose questions can be answered based on a single paragraph, they often fail to retrieve the required evidence for answering multi-hop questions. For example, the question in Figure 1, multi-hop QA, Young 2018, usually requires finding more than one evidence document, one of which often consists of little lexical overlap or semantic relationship to the original question. However, retrieving a fixed list of documents independently does not capture the relationship between the evidence documents through bridge entities that are required for multi-hop reasoning. Recent open domain query methods learn end-to-end models to jointly retrieve and read documents. These methods, however, face challenges for entity-centric questions since compressing the necessary information into embedding space does not capture lexical information in entities. Cognitive Graph 2019 incorporates entity links between the documents for multi-hop QA to extend the list of retrieved documents. This method, however, compiles a fixed list of documents independently and expects the reader to find the reasoning paths. In this paper, we introduce a new recurrent graph-based retrieval method that learns to retrieve evidence documents as a reasoning path for answering complex questions. Our method sequentially retrieves each document, given the history of previously retrieved documents, to form several reasoning paths in the graph of entities. Our method then leverages an existing reading comprehension model to answer questions by recreating the retrieved reasoning paths. The strong interplay between the retrieve model and reader model enables our entire method to answer complex questions by exploring more accurate reasoning paths compared to our other methods. So figure 1, an example of open domain multi-hop question from HotpotQA. Paragraph 2 is unlikely to be retrieved using TF-IDF retriever due to little lexical overlap to the given question. So the paragraph 1, wait a minute, the question is, when was the football club founded in which Walter Otto Davis played at center forward? So they look up Walter Otto Davis paragraph, which describes, that it says that he played center for Millward for 10 years and so. And then, the multi-hop needs to find Millwall, and they find second paragraph which says that the Millwall Football Club is a professional football club in Southeast London founded as Millwall Rovers in 1885. So here we have the answer, right? We have the 1885, that's the answer. and we needed to do one more hop than just the one. So TF-IDF wouldn't answer this question. To be more specific, our method and figurative constructs Wikipedia Graph, paragraph graph using Wikipedia hyperlinks and document structures the neural relationship between the paragraphs. Our retriever trains a recurrent neural network to score reasoning paths in this graph by maximizing the likelihood of selecting the correct evidence paragraphs at each step and fine-tuning paragraph BERT encodings. Our reader model is multitask learned to score each reasoning path according to its likelihood of containing and extracting the correct answer phrase. We leverage the data augmentation and negative example mining for robust training of both models. Our experimental results show that our method achieves the state-of-the-art results on HotpotQA full wiki and HotpotQA the structure settings. Young 2018, outperforming the previous state-of-the-art methods by more than 14 points absolute gain on full wiki setting. We also evaluate our approach on Squad Open 2017 and Natural Questions Open 2019 without changing any architecture design, achieving better or comparable to the state-of-the-art of the art, which suggests that our method is robust across different datasets. Additionally, our framework provides interpretable insights into underlying entity relationships using multi-hop reasoning. Related work. Neural open domain question answering. Most current open domain QA methods use pipeline approach that includes retriever and reader. Chain incorporates TF-IDF based retriever with a state-of-the-art neural comparison model. Retriever is guided by entity links. Most relevant to our work are recent studies that tend to use entity links for multi-hop open domain QA. Cognitive graph retrieves evidence-based documents offline and trains a reading comprehension model to jointly predict possible answer spans and net hop spans to extend the reasoning chain. Instead, we train on a retriever to find reasoning paths directly. Multi-step iterative retrievers. Similar to our recurrent step retriever, multi-hop step retrievers explore multiple evidence documents iteratively. Multi-step reasoner 2019 repeats the retrieval process for a fixed number of steps, interacting with reading comprehension model by reformulating the query in latent space to enhance retrieval performance. Oh yeah, I think I forgot to read the authors. So the authors were Asai, Hashimoto, Haji Shiziri, Zohar, and Xiong from University of Washington, Cells for Research, and Allen Institute for Artificial Intelligence. Just not to forget to mention them. Okay, so related work, we went through related work quickly. We'll need to leave soon. Open domain question answering to Wikipedia Graph. Okay, so this paper introduces a new graph-based recurrent retrieval method that learns to find evident documents as reasoning path for answering complex questions. We then extend an existing reading comprehension model to answer questions given a collection of reasoning paths. Our method uses strong interplay between the retrieving and reading steps, such that the retrieval method learns to retrieve the set of reasoning paths to narrow down the search space for our reader model for robust pipeline process. Figurative sketches the overview. We use Wikipedia Open Domain QA, where each article is divided into paragraphs, yielding 2 million paragraphs in total. Each paragraph piece is considered as our retrieval target. Given a question, our framework aims at deriving its answer by retrieving and reading reasoning paths, each of which is represented with a sequence of paragraphs. We formulate the task by decomposing the objective into retriever objective that selects reasoning paths relevant to the question and reader objective that finds the answer. Our method learns to retrieve reasoning paths across a graph structure. Evidence paragraphs for a complex question do not necessarily have a lexical overlaps with the question, but one of them is likely to be retrieved, and it is entity mentions and question often entail another paragraph, for example, figure 1. To perform such multi-hop reasoning, we first construct a graph of paragraphs covering all Wikipedia paragraphs. Each node of Wikipedia graph represents a single paragraph PI. Constructing Wikipedia graph, hyperlinks are commonly used to construct relationships between articles on the web, usually maintained by article writers, and are thus useful knowledge resources. Wikipedia consists of internal links to connect articles. We use hyperlinks to construct direct exchange, and we also consider symmetric within document links, allowing a paragraph to hop to other paragraphs in the same article. The Wikipedia Graph G is densely connected and covers a wide range of topics that provide useful evidence for open domain questions. This graph is constructed offline and is reused throughout the training and inference for any question. So graph-based recurrent retrieval. So general formulation with recurrent retrieval, we use recurrent neural network to model a reasoning path for the question. At a T step, our model selects a paragraph among candidate paragraphs. CT is given the current hidden state H of the RNN. The initial hidden state is embedded of any question or paragraph based on the parameterized vector. We use paired and class token representation to independently encode each candidate paragraph PI along the queue. We then compute the probability that PI is selected. The RNN selection procedure captures the relationship between paragraph in the reasoning path by conditioning on the selection history. The process is terminated when end of evident symbol is selected to allow it to capture the reasoning path with arbitrary length given each question. More specifically, the process of selecting PI at the TAFE step is formulated as follows. Okay, so let me read this once more. The initial hidden state is independent of any question or paragraphs, and based on parameterized vector, we use Baird's class token representation to independently encode each candidate paragraph along with question. We then compute the probability of PI conditioned on HT. That PI, the paragraph I, is selected, and HT is the hidden state of the RNN. The RNN selection procedure captures the relationship between the paragraphs in the reasoning by conditioning on the selection history. The process is terminated when end of evident symbol is selected to allow it to capture reasoning paths with arbitrary length given each question. More specifically, the process of selecting PI at the TAFE step is formulated as follows. PI, Baird class, question PI. Yeah, so they take Baird for classification. And they always, for each paragraph, they take probability of the Baird classifying it as, I guess, as a useful, as for retrieval. And then they construct the condition probability, sigma function of the Baird probability times the previous step plus some bias, and then H plus hidden state T plus 1 is then RNN operating on the HT and W1. Right. Beam search for candidate paragraphs. So the beam search for candidate is computationally expensive to compute equation to over millions of possible paragraphs. Remote for retrieval of some personal proof for entity-centric questions such as quad. since it does not explicitly maintain lexical information. To navigate our retrieval in the large-scale paragraph effectively, we initialize the candidate paragraphs with the TF-IDF based retrieval and guide the search over the Wikipedia Graph. In particular, the candidate set C1 includes F paragraphs with the highest TF-IDF score with respect to the question. We expand CT by appending end of evidence symbol. We rationally use beam search to explore paths in the directed graph. We define the score of the reasoning path EPI to PK by multiplying the probabilities of the selecting paragraphs. The beam search outputs top P reasoning paths with the highest score to pass the reader model. Right. Okay, training of the graph-based recurrent retrieval. Training with graph-based recurrent retrieval data augmentation. We train our retriever in supervised fashion using evidence-based parent, okay, which is here with multi-hop, ground truth reasoning. We augment the training data with additional reasoning paths, not necessarily the shortest paths that can derive the answer. In particular, we add a new training graph by adding a paragraph PR that has high TF-IDF score and is linked to the paragraph P1 in the ground truth path G. Adding these new training paragraphs helps at the test time when the first paragraph in the reasoning path does not necessarily appear among the paragraphs that initialize the Wikipedia search using heuristic TF-IDF retrieval. Negative examples for robustness. Our graph-based recurrent retrieval needs to be trained to discriminate between the relevant and irrelevant paragraphs at each step. We therefore use negative samples along with the ground truth paragraphs to be more specific. These two types of negative example, TF-IDF based and hyperlink based one. For the single hop QA, we only use the type 1. Multi-hop QA, we use both types, and type 2 is especially important to prevent our retriever to be being distracted by reasoning paths without correct answer spans. We typically set the number of negative examples to 50. Loss function. The sequential prediction task, we estimate PI independently, equation free, and use cross entropy to maximize the probability values of all possible paths. Note that using the widely used cross entropy loss with the softmax normalization over CT is not desirable here. Maximizing the probabilities G and G are contrary with each other. More specifically, the loss function of G and the taste type is defined as follows. Okay, well, C is negative sample, describable, V is multiple. The loss is also defined with respect to the okay, so what is the retrieval loss is minus log probability PT given hidden state and minus the log of 1 minus P P prime in C T prime where CT is set of negative example. So they have these. So the loss is how I guess how much how much bigger is the probability of retrieving the correct one minus the contrastive ones. Log likelihood, in sense of log likelihood. Okay, HotpotQA. HotpotQA development set result QA and SP support fact prediction result on HotpotQA full wiki descriptive syndromes. Okay, so the our reader bad base. So their reader does on QA F1 score 73. That's much better than the transformer XH. I mean, from 62 to 73, it's quite a huge jump. And in metric EM on the QA, it does from 50 to 60, seems quite large jump. And then the odd data sets, the jumps down SP, this guy, full wiki. On the distractor benchmark, they seem to do also very, very well. On the full wiki in the SP settings, supporting fact prediction, they don't actually do that much better, but on the QA they do. And in the distractor settings, they do very well. So overall results, table 1 compares our method with previous published methods on HotpotQA dataset. Our method significantly outperforms all previous results across evaluation method under the both full wiki and distractor setting. Notably, our method achieves 14 F1 and 14 EM gains compared to the state of the art. Gains over concurrent transformer XH model on full wiki. We see that our method, even with the base BERT configuration, really significantly outperforms our previous QA scores. Moreover, our method shows significant improvement in predicting supporting facts in full wiki settings. Where do I say about the destructor? Alright. Okay, I will have to go. I will read the conclusion once more, and after that it's over, man. So this paper introduces new graph-based recurrent retrieval methods using paths over Wikipedia Graph to answer multi-hop open domain questions. Our retrieval model is to sequentially retrieve evidence paragraphs to form reasoning paths. Sequentially, our model reader ranks the reasoning paths and determines the final answer as the one extracted from the best reasoning path. Our experimental results show significantly advanced the state of the art on HotpotQA by more than 40 points absolute gain on full wiki settings. Our approach also achieved the state of the art performance on squad open and natural question open without any artificial changes, demonstrating the robustness of our method. Our method provides insights into underlying entity relationships and discrete reasoning paths and are helpful in interpreting our framework reasoning process. Furthermore, involves end-to-end training. Future work involves end-to-end training of our graph-based recurrent retrieval and reader for improving upon our current two-stage training. Okay, thank you very much. Please dislike and subscribe. And yeah, I hope to see you next time. See you guys.